All right. Okay. So nobody's in class just yet, but I am going to continue with this class, I think. Okay. So you guys will also see I adjusted the slides for this module, or rather I made some amendments. All right. So let's quickly go through this. So I think last time we looked at how we trigger an SCR on and off. And yeah, and I was about to have us look at a few examples. Okay, so I see there is some issues here on these slides, but anyways, so yeah, so let's quickly take a look at some of these examples. So the examples that we're going to take a look at, it has to do with, I don't have everything on the slide, so I'm going to use the textbook here as well to assist. So the example that I have here on the slides is basically related to the temperature, or rather, basically the temperature characteristics or power dissipation characteristics of SCRs, which is directly, which will be directly related to the temperature of the SCR. So you guys will see that we have our output power, or rather the power dissipated by our component, and then we have our difference in temperature. So T1 would typically be the temperature of your SCR, or your junction temperature. So in this case, it's 125 degrees C with 40 degrees C ambient conditions. Now, you can, however, yeah, so this is basically what we want to calculate here is how much power our SCR will have to dissipate into the environment. We're also given the thermal resistance of the heatsink as well as that of the the Thyristor SCR itself. So SCR 1.8 degrees C per watt, and then 2 degrees C per watt for the heatsink. So we add those together, that gives us a thermal resistance of 3.8 degrees C per watt. And then dividing this by our, or rather dividing this into our temperature difference between the ambient and junction temperature, that's then going to give the power dissipated by our SCR. So in this case, 22.37 watts. It is possible to have, so if you want some buffer between, so if you don't want to operate right at the junction temperature, you can set this temperature lower. That does mean that you will have, you can have it lower, but it means you have to basically adjust your, what you call it, the thermal resistance, or maybe adjust your power dissipated by a component as well. But I think you don't really have control over the power, but you can have control over the thermal resistance, so you can use a better or bigger heatsink. So there's a few things that one can do to adjust this. Right. Then we can take a look at, okay, before we go on to DC line commutation, there are actually other few things that I would like us to look at. So hopefully tonight we can put this chapter to bed, because this chapter with the new content is somewhat longer than what it used to be. So I'm going to go over to the textbook. Right, okay, so while we're waiting for the textbook to render and load, so a lot of the examples that we're going to take a look at now have to do with the ratings of SCRs, so basically calculating the SCRs, like power dissipation, determining how much current you can let through it. Let's see, let me get it here. Right, so another thing that we haven't looked at is limiting. So I think in the previous class I did speak of the effect of high current rise. Now, yeah, so if the current rise is too high, so meaning your current changes too quickly through your SCR, that can actually cause the SCR, yeah, so it can actually cause the SCR to not be able to dissipate the power fast enough, or the heat fast enough, and then you can actually go over that heating limit, or heating rating, or temperature rating rather, of your junction. So typically the junction for most semiconductor devices can handle up to 125 degrees C. Go over that, you will damage the component or destroy the component. Right. So if you have a very fast rise in current, that's also going to coincide with a fast rise in temperature, but also not just fast, but a very high rise in temperature as well. Okay, so I'm just going to quickly share my screen. So yeah, so as you guys can see, in order to limit the rise in current, or rate of change in current, we can make use of an inductor to do that. So yeah, so the example that we have here, there is a quite a few typos in the textbook. Yeah, guys, I know it's to the frustration of us all here, so just bear with me. I don't know how the author typed formulas, but that should be just square root 2 times the line voltage, not the square root of 2 times the line voltage. Right, so that is incorrect. You guys will see, especially in this chapter, quite a few of those mistakes made here. Right, so for example 7.1, we need to go calculate the value of an inductor to be placed in series with the load if it's fed from a 300 volt AC supply. And this is to limit the rate of change of anode current to a value of 120 amps per microsecond. Right, so in the first case, we don't have any tolerance, meaning, so we just take everything, plug it into our formula, and we get an inductor of 3.45 microhenries that we need. Now, in the case of accounting for a tolerance of 0.8, 80%, I think. Yeah, I'm actually thinking here the textbook is kind of just giving us the best case scenario here. So where you have a smaller inductor. I would say in order to, yeah, I think that should actually be multiplied with 1.2. So for a 20% increase. But in any case, so we have a tolerance of 80%. So basically just take the inductor value times 0.8, and that's going to give you 2.83 microhenries. So yeah, so just do this for what you call it, for the exams. So yeah, so keep it that way. You guys will see that that is 2 times 300, and then taking the square root of that whole thing. If you guys are going to plug into your calculator, you guys will see that you will not get that answer as it is typed in here. So it's actually just square root of 2 multiplied by 300, right? Not the square root of 2 times 300, right? Like I said, you guys will see this typo, especially in this chapter. I haven't found a place where it's been done correctly. So yeah. Okay, and then yeah, so another thing that I don't have in the slides, I believe, is the use of a snubber circuit. So snubber circuits is basically yeah, you can have an RC circuit in parallel to your SCR with a diode. Essentially what that does is to limit that. We also talked about the change in voltage across your SCR as well. So you don't want that change in voltage to be too steep, because that can actually switch the SCR on. So in order to prevent misfiring or unwanted firing of our SCR, we use a snubber circuit. Right, so yeah, so for a snubber circuit, yeah, so in order to calculate the size of the capacitance here, that's going to be I don't know where that RL is that they talk of. I think it might be, yeah, I think it might be that load resistance up there. Then the snubber here is in series with the load. So yeah, so essentially capacitance, that's going to be where T, I love it how they explain everything else except there's T, time in seconds. Right, but they also don't tell you what time. So there's that VDRM. It's your forward blocking voltage for your SCR. So that's typically then going to be just the maximum of your supply voltage divided by your change in voltage that your SCR can handle. Yeah, so it's your maximum rate of change of anode voltage. And didt is your maximum rate of change of anode current. Right, so that's then the value for RS, and then you can calculate the value of RC using the load resistor. And yeah, so your load resistor, yeah, I think it's that unlabeled resistor there. And yeah, so basically, then we have another example here. So pretty straightforward. It's basically, they ask us here to calculate the capacitor and resistor RS with a given load resistance of 30 ohms. And they also give us the forward blocking voltage. So typically your forward blocking voltage is usually going to be your, it's going to be the maximum of your supply voltage. So it's basically the voltage that the SCR needs to be able to block in forward conduction mode, or rather, if it was a diode, if you apply forward voltage on it, it needs to be able to block 700 volts in this case. Yeah, that is with so that is without applying a gate signal. So when you apply a gate signal, that forward voltage then becomes 0.7 volts if it's a silicon SCR. Right, so as you guys can see, pretty straightforward. Take the formulas, just substitute. You are given everything. So maximum rate of change of voltage, maximum rate of change of anode current. And yeah, and remember, this is 50 amps per microsecond. I'm actually baffled a little bit here on how they do the calculations here, because it's, let me just see here. So that is 40 volts per microsecond or 40 megavolts per second. All right, okay, but they keep the microseconds here. So, okay, so that actually makes sense. There's a bit of a problem here, actually. I think the calculations are done incorrectly. But look at this. That needs to be 40 divided by 10 to the minus 6. Yeah, so there's a problem here. This is not correct. Because as it is, as it's here now, actually, maybe they calculated this correctly, but the substitution here is done incorrectly. That should be 40 divided by. So it essentially becomes 40 times 10. Yeah, so it becomes 700 times 10 to the 6 divided by 40. Right. Also, there is a, I mean, actually, then it actually is, in a way, still correct in that manner. Now, this is a bit of a problem because there's no way you're going to get 17.5 microseconds out of that. That should be 40 times 10 to the power of 6. All right, so there are some other examples that I also want us to look at. So, I mean, we have looked at the trigger circuits. I think the new content does go a little bit into more detail on this. So this is also still ties into chapter 1 as well. Right, so actually, yeah, I think we can maybe take a look at this example. I think if I can get an exercise, then we can take a look at this. So this has to do with, and I think we have talked about it very briefly last week. Is the fact that you have a latching current. Now, SCRs, if I can maybe just explain here. So you have a minimum current that SCR needs to have flowing through it for it to to stay on. Now, if you don't manage to get that, so let me maybe explain here with the help of a drawing. So if we have, let's say, the latching current of our SCR is maybe, for argument's sake, 10 milliamps. Right, so let's do it. So I'm just going to do this. So there's your axes, and let's say the latching current of our, come on, latching current of our SCR is around about there. So if we say that's maybe 10 milliamps, so that's your so your latching current. So if you have, for instance, now a circuit and the current through your circuit, so let's say you have a pulse. I'm also going to draw the pulse here as well. So let's say we have a gate pulse applied to your SCR, and your load current, so let's say this is your load current. So if your load current by the end of the gate pulse, if that hasn't reached 10 milliamps yet, right, your SCR is going to switch off. So there, the reverse recovery bit there as well. Right. But if we, let's say if we increase the pulse length now for this example a little bit, by quite a bit, actually doubled it. So now, if we try and keep the rate of current change the same, so that the current then goes through our SCR. So the moment we get to this point where the current, your load current is equal to your latching current, the SCR will continue conducting this current. So if your load current then for some reason goes stable like that, or you have a DC current, do this. Okay, so let's say that's your load current. So once you reach that point, then the SCR will stay on. Yeah, so it will stay on as long as the your voltage across the SCR is forward biased. Right. Okay, so that's pretty much what's done there. So we can actually quickly take a look. So we can quickly take a look through this example. So essentially what we have here is we're told that we have a specific SCR with a latching current of 50 milliamps. And we're told that the pulse that fires the SCR has a width of 40 microseconds. So there's another way you can actually reach that latching current is by actually putting another, how can I say, load in parallel with your already existing load. All right, so we need to go determine whether the SCR will be fired and whether it will stay on in this configuration. Right, so this is not necessarily just for RL circuits. It can also be an RC circuit in this instance as well. But then you have to have then you need to know how to calculate your time constants, and you need to know what the formulas and stuff is for the capacitor circuit. Then in that case, in this case, we have an inductor circuit. So yeah, so as you guys can see, you can actually go and check whether or not your circuit is going to be, or whether your SCR is going to stay on. So at first we go calculate what the maximum current is. That's 2.5 amps for this example. The time constant for the circuit is 0.01 seconds. Then we can substitute everything into our equation for instantaneous current. And yeah, so the time that we have is 40 microseconds for our pulse, and we have 10 milliseconds of time constant. We substitute it in, and we see we only reach a current of 9.98 milliamps. Now 9.98 milliamps is quite a bit away from 50 milliamps. So we need to somehow get an additional 40 milliamps being drawn by the load side, so that the SCR will stay on after 40 microseconds. Now, the one way we can do this is by adding a parallel resistance to the load or to the circuit. And that is then, yeah, so that resistance will need to give us that additional 40 milliamps. So yeah, so our supply voltage, 120 volts, divided by 40 milliamps, that's going to give us a 3 kilo ohm resistor that we need to place in parallel here. And yeah, and that is essentially then going to provide you, and then you can go further prove. So I think that's actually a last step that's missing here. You can then further prove, okay, your SCR is going to stay on. All right. And then we also get to calculating the peak and RMS currents for SCRs. Now, the current ratings for SCRs, actually for like most semiconductor components, you have forward average, yeah, so you have an average forward current, an RMS value that the component can handle, but there's also things like current pulses and such of much higher value that these components can handle. So, for instance, some of the ratings, you might have a component that can handle 10 amps continuously on a normal operation. But if you were to apply 10 microsecond pulse to the component, then that component can actually handle currents much higher than the average operating current. But then that's just a maximum current, and only for 10 microseconds. Go beyond that, then you're exceeding the average current limit that that component can handle. Yeah, and as you guys can see, it's basically temperature dictating the amount of current that can flow through the SCR as well. So yeah, and also if you switch an SCR the whole time on and off, that's also going to give you temperature rise, and yeah, so uh, the rate at which your current changes again, that's going to influence that. So I think we can take a look at this example as well. I think this is the first time I've actually seen this example worked out nicely in this text in the textbook. Only problem here is they do not explain very well. Ooh, this is gross. So they just substitute the degrees in here, well, while we have radian values like 2 pi and pi. I actually want to quickly just see, for interest sake, I'm going to get the values here that they get by just doing that, because in um, the previous iteration of the book, that was indeed not the case. I had to convert degrees to radians first, or just change pi to 180. That also works. Yo, okay, they did a very gross thing here. We broke some mathematical rules here. Right, so they calculate the peak current. I don't know how you can have a peak current of 4.2 amps and a max of 10, or a mean of 10. If you have a max of 4.2, I don't know how you're going to get an average of 10 amps. Not even reaching the average. Okay, so guys, another mistake in the textbook. Don't follow this example. I'm going to demonstrate with an exit. You know what? Let's fix the example. Right, so I'm going to take this here. So basically what they want us to do is they want us to calculate the RMS here. I'm also going to make copies of the formulas. I actually want us to do another one of those examples with the latching current, but I think I'm going to move on from there. The example in the textbook is pretty sufficient. There's not really anything else that can be asked there. Okay, so big mistake in the textbook. Right. Okay, so a little bit of a rule of thumb. Your maximum current will always be bigger than RMS. And this is also for voltage as well. You guys can apply this rule. It's pretty much a universal rule. Just a way to check your answer. So maximum current will always be bigger than RMS, and RMS will always be bigger than average. Right, so that means that your maximum current will always be bigger than RMS and average. Okay, so yeah, that's something we need to keep in mind. So how it's done in the example of the text, in the textbook, it's not correct. Right. So one of the things is that you guys need to keep in mind here, and I think there is a detail missing from this table. This angle needs to be in degrees, the units. Right. And I think they do state it in the example. I'm just going to jump back here real quick. I mean, the drawing of the poles here should actually give you an indication that they actually are working with degrees. So we will have to go and change this. Right. Okay. So another thing here is that this, for some reason, this whole, they want you just to calculate the RMS. And this means now you now need to go calculate the peak and then RMS. You can actually change this into one formula if you want. I think it's going to be a little bit easier. So you can actually change the RMS to, you can take the mean current, which is, or the peak current, and substitute this into there. That will then give you, let's say the RMS will now be the average or mean times 2 pi over theta. That's then going to be square root theta over 2 pi. Okay, I hope you guys can see we are sitting here with an interesting situation here. So we can actually take that and that will cancel out. That leaves us with the average times square root of theta divided by theta. So yeah, so there is another thing that we can do here. We can multiply by 1 square root, so square root of theta, square root of theta, and that will then give us the average. That's going to be theta times square root of theta. That's then going to be theta up top. Those are going to cancel. So your RMS is essentially your average divided by square root of your angle. Right. So one thing that the book gets very wrong is the fact that you have to work with radians. It's not a degree value that you have to work with. It's radians. Right. So you have to convert these numbers to radians in order for this thing to work. Just actually something that's a bit bothering me a bit about this formula, because I think the previous formula looked a little bit different. Remember pi still being present, but anyways. So yeah, so that's what we have. Yeah, okay. So we can rewrite our angles into radian form. So 15 degrees. Yeah, 30 is going to be pi over 6. Then 15 degrees is going to be pi over 12. I mean, we can test it. 180 degrees divided by 12. It's 15, okay. 30 degrees, we have 60 degrees is going to be pi over 3. 110. Let's think here. Yeah, so we can actually write that as well. So 110 out of 180 times, actually no, we want the radian value. So you're going to multiply that. So if you want the radian value, multiply by pi over 180, I believe. Yeah, pi over 180. So you want to get rid of the degrees. So that is 110 divided by 180. So that, okay, so we can actually just write it as 110 pi over 180. That can actually just become 11 over 18. That's then going to be 30 degrees over 180. That is 7 pi over 6. And then 180 is, well, pi. So then you can actually go and calculate the current for each. So I'm just going to use the formula that I derived here. So can just do that repeatedly for each situation there. So that is our average current. That's been given to us here on the top row. So that is an average of 10 divided by the square root of pi divided by 12. Okay, so that's going to give us a maximum current here. Let me maybe rewrite this a little bit. So this is our angles. This is then going to be your maximum or peak current. Right, so this is then going to be 19.544, which makes a bit more sense. I'm just going to write here that this is an amps, all then we don't have to write the units in every instance. Okay, and then the next is 14 amps divided by what is it, square root of pi divided by 6, and this is going to give us a maximum current of 19.348, and then it's 18 amps divided by the square root of pi divided by 3. That will give us 17.59 amps. Then we have 20 divided by the square root of 11. Yeah, so 11 times pi divided by 18. So that whole thing under the square root. And that's going to give us 14.434. This is actually why I don't like this, because I believe there is something missing here. This is our RMS current that we are calculating. Peak. Okay, and then we have, what is it, 24 amps divided by, yeah, so if we were calculating the peak, yeah, so we're calculating RMS, not the peak. Okay, so that is then 24 divided by square root of 7 times pi divided by 6, 12.536. And then for the RMS, in this case, divided by square root pi, which is going to be 15.797. Right, and I think, yeah, if we go take a look at the textbook, they probably going to get like almost to 0 amps toward the end here. Yeah, I don't know how you can have a peak of 1 amp, but an RMS of 5.1 amp. That is physically impossible. So yeah, any case, the calculations here are not right. So you have to convert these degree values to radian values. I mean, the pi should actually already be an indication that you're working with radians. This is not correct. Right, so then there's also some more temperature calculations. So I'm going to skip this for now. So there's another one. So this is has to do with, so example 7.6 has to do with when an SCR is turned on from cold conditions. So there is, so switching it on from cold conditions, you're going to get essentially a transient period for the temperature as well, whereby the SCR, so for this particular example, is going to dissipate 1,400 watts of power for 20 milliseconds. And yeah, at switch on with an ambient temperature of 20 degrees C. And yeah, so we need to basically which is usually what is usually done here is you also want to check if your SCR is actually going to, I want to say, survive the process, right? So your what you call it, your thermal impedance. So that is that 0.02 there. So that's then your temperature rise divided by power lost. So we're more interested in the increase in temperature of our SCR. So if we take a look at this, your temperature rise is then basically ZTH, so that's 0.02 degrees C per watt multiplied by your power lost. So again, typo in the book, which should actually be 1,400 watts, but okay, who cares? That then is gives you 30 degrees C rise in temperature. And now we can actually calculate the junction temperature. So that's just the ambient plus the rise, and that gives you 50 degrees C. So we can actually say something from this. So because the junction temperature is less than 125, which is typical for semiconductor devices, because this is less than 125, the SCR is still protected. So you still don't need a heatsink in this instance for the SCR. Right. Oh, because we didn't reach the junction temperature. So yeah, so that's a typical follow-up question that could come from. All right, so I'm just going to quickly go through the slide. So we still have DC line commutation to look at. So yeah, so this is actually quite a lot of reading. So it's essentially, yeah, so the practical implementation for DC line commutation is usually going to take the form of what we call a DC chopper circuit, which is a form of DC to DC conversion or DC to DC supply. So you're essentially going to have the two SCRs alternating between being off and on, and the timing between the two is essentially then going to be determined by the size of this capacitor and the charge and discharge relationships between R1 and R2 here. All right, so that's then going to determine the timing on when T1 and T2 is going to be on or off. There is also an example in the textbook in terms of calculations to calculate the size of the capacitor and also the on and off times for the two thyristors. Then we also have resonant commutation. So series resonance commutation and parallel resonance commutation. I see my text there is a bit squonked there by the picture. I should have actually checked that. Essentially, yeah. So essentially what happens here is you're going to have a, so in series resonance, you're going to have your capacitor inductor combo in series with each other. That's in series with the SCR. And the circuit needs to be underdamped so that, so essentially what you're exploiting here is the reversal of current in the circuit. So remember, with an underdamped circuit, you have an oscillatory response. So if you take a look at your transient response, it looks something like that. Now so this is if we look at the voltage, but in the time, during that time, for instance, the current is going in reverse, and that's going to cause the SCR to switch off. Parallel resonance, so in this case, you have the capacitor inductor in parallel with the SCR. See that the two components are still in series. Let's take note of that. And in this case, so in this case, your component values need to be such that the circuit will be critically damped. Right, so there is some caveats to this. So for one, if the resistance is too low, the load current could be greater than the oscillating current, right? So which means that the SCR is not going to switch off. And if the resistor is increased, the charging of your capacitor would be too slow, right? Making your minimum off time too long. Right. Okay, so there's an example of how the chopper circuit works. I'm not going to go through this. It's essentially just to go and calculate the size of the capacitor here. And then there's also the different types of rectifiers. There's quite a lot of reading here on, oh yeah, and this is the main advantages of using DC. I believe this is DC motors. So yeah, so there's some advantages in using them over AC. I'm not going to spend too much time here. All the formulas here are in the slides. I don't see the textbook having formulas, but yet the exercises have, yeah, yet with the exercises there are exercises on doing calculations with the circuit. So I have included the formulas for you guys there still. And also take note where there's a delta supply, that can also be a Y or star supply. And where there's a star supply, that can also be delta. Right, so it's not that an uncontrolled three-phase bridge rectifier can only be supplied by a star connected transformer or star connected generator. It can also be powered by a delta connected supply as well. Right. Okay, same with the delta, can, like I said, can be star. Right, so it doesn't matter. It does matter though when you working with either phase or line voltage. Right, so if you're given phase voltage, you know you're working with a star system, and you will have to convert the phase voltage to line voltage by multiplying with square root 3. And if you're given line voltage, then yeah, then you don't really care about whether you're working with star or delta. Then we have cycloconverters. Again, guys should go read through this. Essentially, what you have here is something very similar to, I want to say almost a rectifier, but in fact, you have your thyristors turning on and off. So you have let me maybe do this. So you have a set of thyristors that will create the positive part of your waveform. So what a cycloconverter does, it's almost it's not really a type of inverter, but it is some form of frequency control that can be used to control the speed of an AC motor. Now, cycloconverter, what it does, it lowers the frequency of your input signal. So you could maybe, let's say, input 50 hertz and then get a 20 hertz output by controlling your switching sequence here. So as you guys can see, those two, that set of two thyristors will then give you the positive part of your output waveform. So your output is then going to be the average of those chopped up waves. Yeah, so well, actually, yeah, you're going to see on the output, you're going to see the blue wave, but if you put a filter on the output side, you can get that red wave. And then for the negative part, essentially, you're then going to just switch those to during that time, so you can get your negative part of your output waveform. And again, the average of that is going to give you that. So yeah, so depending on how you do your switching sequence, you can you can reduce the frequency or keep the frequency the same. You will not be able to increase the frequency, however. That you have to do with some in between phase. If I can quickly go back here, so you guys will see there is a basic diagram here of an inverter setup. So is this an inverter? Yes, kind of. A very basic one, but basically an inverter you can use actually to increase or decrease the frequency and thus control your AC machine's speed. So that's actually how you can control the speed of an AC machine, is by changing the frequency. Right. You're not really going to change the speed by changing the voltage. All right. Yeah, I just want to see. Okay, so there is a cycloconverter for a three-phase system. And it does seem that you will need a star connected transformer, star connected supply for this, just so that your load has a neutral to connect to. And then there's some calculations, or rather some formulas that you guys can use. Again, the formulas in the textbook are incorrect. So in the textbook, they do this, which is wrong. Otherwise, you're never going to get your answers. You guys can go and test this as well. So yeah, so there's that. So that's for cycloconverter. So that alpha is just your what is it? Your firing angle. Yeah. So there's also a single phase bridge inverter. So typically, yeah, so what an inverter actually does, it takes a DC source and changes it to an AC output. I believe the examples that we have in the textbook, from what I've seen, are all quasi square wave. So basically something like this. Right, so that is if you have two inverters. So you can have two single phase inverters supplying the same load. Just, I think in this case, they're like 90 degrees phase shifted from each other to build that. So as you guys can see, it's almost, yeah, so if you add maybe, let's say, a third and a fourth inverter, you can actually make this thing almost resembling a sine wave. And you do get pure sine wave inverters as well. It depends on the switching method that you use. So this is just a straightforward square wave switching method. So you're not going to get a sine wave this way. The one way that you can get a sine wave is by means of PWM switching, which we don't really look at for this chapter. Yeah, so it's PWM and PDM. PDM is pulse density modulation. So by increasing the density of pulses, you're increasing the average. And pulse width modulation is basically using the width of the pulse to change the average. Right. Okay, and then you have your three-phase bridge inverter there. So you can either connect the output in star or delta. And yeah, so there's your output for each phase, or each line actually. And so you guys will also see they are 120 degrees shifted from each other as well, just like we would have with a standard sine wave system, standard AC system. Right, so I know I moved quite fast there. So we get to AC motor speed control. Again, quite a few advantages that we can get with AC motors above DC. So AC motors are actually quite efficient, and they are cheaper than DC motors. They have lower maintenance just due to the fact that they don't make use of carbon brushes, which need to be periodically replaced on DC machines. And also, yeah, so also DC machines. So just think about it for a second. If you have carbon brushes getting worn out, where does that carbon go to? Right, the carbon dust just doesn't disappear. It goes somewhere in your machine, and it can cause issues. Can be a fire hazard. Can cause short circuiting on your terminals if it somehow manages to get into your terminal box. So yeah, so there's a danger. So that's where AC machines are better. AC machines do not have brushes. Make use is in particular induction machines. No brushes at all. Just using the power of magnetism to cause rotation. All right, and then yeah, and then you can also have a wide range of motor designs as well. Okay, so yeah, so if you take a look at an AC drive, so AC drive is essentially an inverter system. So you're going to have a rectifier that basically takes your 50 hertz input AC, changes it into DC. You can also use it to generate power in things like regenerative braking. I see I made a typo here myself. It needs to be the rectifier. So yeah, so you can also use that rectifier unit to push power back into your supply when you use things like regenerative braking. So yeah, so that's actually also a plus there. Usually you can make a bidirectional rectifier by making use of SCR. So if you use, let me maybe quickly go back here. So if you do a fully controlled, yeah, so for instance, fully controlled, so here's a three-phase rectifier, you can actually reverse the DC voltage here on the other end, right? So you can actually reverse the rotation of a machine, or if you want to do regenerative braking, you can allow current to flow in the other direction through your rectifier. So it's actually quite versatile having that. Then you have a DC circuit. So typically you will have some form of DC to DC converter to either step up or step down the voltage while it's in DC. And also to filter out your rectifier output as well. So you don't want the globe. So you have a smooth DC input to your inverter, and your inverter will then typically take that DC power and then output it at usually output at a frequency that's different from your supply frequency. Right, so typically you would either want to increase the frequency, and I see I haven't, oh, last night missed this all, but in any case, yeah, so basically if you need to increase the frequency, this inverter unit is going to allow you then to do that. So if you have 50 hertz in, but let's say you need your motor to be a little bit faster, so um, if we ignore slip, you should have around 3000 RPM on a 50 hertz system. But let's say you require 6000 RPM, which means you will have to double the frequency, and the inverter will then basically allow you to do that. Right, so there are some, so there are various control methods to do this. There's the variable voltage AC drive that you can use to basically drive the motor. I think this is also called I'm not sure, but it's also called I don't know if this is a constant voltage AC drive, but I don't know why it's called a variable voltage AC drive, but we have a constant current AC drive in the book. And the diagram still looks the same from the previous syllabus, and previous syllabus called this a constant voltage AC drive. Anyways, so variable voltage AC drive, so I think it refers to the speed adjustment here. So you're essentially changing your regulating voltage here. And as you guys can see, your frequency control then go into your inverter. And yeah, so the level of voltage that you have here is also going to determine your frequency. Okay. Then you have a PWM AC drive, or pulse width modulation. So essentially, your frequency and voltage control is done directly on the inverter itself. So you're basically just switching the inverter. So changing pulse widths for your with your voltage, and then thus changing the frequency on the inverter. Then you have constant current or current source AC drives. So basically making use of a current regulator. So you're essentially measuring the current going into the inverter, and basically using that then to control your rectifier, and thus control your DC voltage. And yeah, so you can also do your speed and voltage control here as well. So you guys can see, so current is basically, so your output current or your load current is being used here to control the speed of your motor in this case. And then there's your different types of braking. You get what we call plugging, which is basically just taking, so this is, you guys will see some of this is actually more applicable to DC machines, like plugging, for instance. So you basically just take a resistor and short circuit the armature connections. Right, so essentially what that causes is that so you basically disconnect the armature and then short circuit it with a resistor, and that basically causes the armature then to become, your motor then becomes a generator essentially, and the high amount of current within the armature is then going to stop the armature from rotating, again exploiting Lenz's law. So if you guys hopefully you guys still remember Lenz's law. Then regenerative braking. So this is in the case where you need to preserve some energy. So this is typically used or employed in battery operated vehicles. So when you're going uphill, you're obviously then draining power from the battery, and then when going downhill, in order to regenerate some of that power, you can now run your vehicle as so your vehicle's wheels, or so the drive shaft can now act as a generator, and that can then push energy back into the batteries. Right. So that is regenerative braking. Then you have dynamic braking. So this is typically used where you need a rapid slowdown. So something like an emergency stop or something of that nature. And in cases where regenerative braking is also not possible or not safe to do, So if you have the stop button activated for a certain motor, you have a contactor that places a fixed resistor across the armature, very similar to plugging. So plugging is actually the connections are reversed via a resistor. Yeah, and this also disconnects the armature supply. Yeah, and again, using a fixed resistor will result in a linear drop in braking torque with speed. And yeah, so again, Lenz's law acting here, slowing the motor down very quickly. So dynamic braking and plugging are pretty much, yeah, making use of the same mechanics there. Right, guys, so chapter 9, which is, well, actually, I need to change this. This is going to be chapter 8 now. For PLCs, chapter 9 is now robotics. So, yeah, so next class, we'll take a look at PLCs. Ideally, I would like us to take a look at ladder logic. I'm not going to spend too much time on the theory because we don't really have that much time. And then hopefully last class, we can then do robotics. Robotics, there's not really much calculation going on there, but there is some theory and some things to understand there.